एवरीवन, वेलकम टू इंजीनियर्स करियर पॉइंट। इंजीनियर्स करियर पॉइंट में आपका स्वागत है। माय नेम इज चंद्रशेखर। आई एम द फैकल्टी ऑफ इलेक्ट्रिकल एंड इलेक्ट्रॉनिक्स इंजीनियरिंग एट इंजीनियर्स करियर पॉइंट। इंजीनियर्स करियर पॉइंट चंडीगढ़ पे सेक्टर 34 पे लोकेटेड है। हम जून 1 से ऑफलाइन एंड ऑनलाइन गेट का बैच स्टार्ट कर रहे हैं। जो बच्चा ऑफलाइन के लिए चाहते हैं तो आप सेंटर विजिट कर सकते हैं। जिस बच्चे को ऑनलाइन चाहिए, जो डिस्क्रिप्शन में दिया हुआ फोन नंबर पे आप कॉल कर सकते हैं। हमने एक सीरीज स्टार्ट किया है, वो है 50 इंपॉर्टेंट टॉपिक्स फ्रॉम ईच सब्जेक्ट फॉर गेट एग्जामिनेशन। इन दिस हम क्या कर रहे हैं, पहले टॉपिक आपको पढ़ाएंगे, उसके बाद वो वाला टॉपिक के ऊपर जो क्वेश्चंस प्रीवियसली गेट में दिया हुआ है वो वाला क्वेश्चंस आप आसान से सॉल्व करेंगे। तो आज मैंने स्टेबिलिटी ले रहा हूँ। स्टेबिलिटी इज अ वेरी गुड टॉपिक एंड वेरी इंपॉर्टेंट टॉपिक। In fact, it is a simple topic in one direction and it is a difficult topic in another direction. तो मैं आज वाला क्लास में थर्ड ऑर्डर, फर्स्ट ऑर्डर, सेकंड ऑर्डर, थर्ड ऑर्डर, फोर्थ ऑर्डर, ये चार ऑर्डर्स के लिए शॉर्टकट्स बताने जा रहा हूँ। द शॉर्टकट्स मींस आप जनरल प्रोसीजर में जाने से एक क्वेश्चन को सॉल्व करने में आपको 2 मिनट लगेगा, लेकिन शॉर्टकट यूज करने से बस 30 सेकंड्स में आपको आंसर आ जाएगा। तो ऐसा डायरेक्शन में हम जा रहे हैं। तो और टॉपिक इज स्टेबिलिटी। तो स्टेबिलिटी आपको पता है, टू फाइंड स्टेबिलिटी we use Routh-Hurwitz criteria for higher order equations. Routh-Hurwitz criteria. So our topic here is, see, I'm teaching in stability. I'm teaching in the context of GATE examination, not for I can say engineering services examination. If it is for engineering services examination, we have to learn complete the theory also, and we have to write descriptive questions. But in GATE examination only, numerical answer type or MSQs or MCQs will be asked. So here the concept and solving the question, that way we are going to learn. Engineering services objective examination के लिए it will be useful for you, right? So come here, all of you, stability. What is a stable system? That is very simple. A stable system is a system if its impulse response or natural response decreases to 0 as time t tends to infinity. This is the basic definition of stability. Yes, stable system. What is a stable system? Stable system. Yes, it is if the impulse response or natural response of a system decreases to 0 as time t tends to infinity, then that system is said to be said to be stable. Said to be stable, right? So this is the basic definition of stability of a system in time domain. But it's not possible to find the nature of impulse response or natural response with respect to t tends to infinity for higher order systems. So what we are doing then, if you apply Laplace transform to any impulse response, you'll get a transfer function. If you apply Laplace transform to any impulse response, you get a transfer function. Once you have transfer function, yes, transfer function is equal to c of s by r of s. The general transfer function is g of s by 1 plus g of s into h of s. If I take negative feedback into consideration, the characteristic equation of the system is 1 plus g of s into h of s is equal to 0. Now the roots of the characteristic equation are called as closed loop poles, right? The roots of the characteristic equation are called as closed loop poles. The stability from poles point of view is all the poles, if all the poles of a given system lies in left half of its plane, then that system is said to be stable. Yes, what is the, see, this definition is in time domain. Yes, if the natural response or impulse response of a system decreases to 0 as time t tends to infinity, then that system is said to be stable. The same if you convert into frequency domain or S domain, I can say that. So this is important for us. So the frequency domain definition and its understanding is very important. Then we are going to extend this one with the Routh-Hurwitz criteria, right? Finding stability. Yeah, stable system. What is the definition of a stable system? Yes, if all the poles of a given system, yes, lies in left half plane, then the system is said to be system is said to be stable, right? Then the system is said to be stable. Now let me take few examples, then I'll tell you why we are going for Routh-Hurwitz criteria. Yes, suppose system 1, this is a system 1 example is given, characteristic equation is equal to s plus 2 is equal to 0. S plus 2 is equal to 0. What is the order of a system? First order, only s is there. If it is s square second order, s cube third order, how many poles it is going to have? One pole. Yes, that is s is equal to minus 2. That s is equal to minus 2 is there in the left half of s plane. Simply we can say that it is stable. Simply the system is stable. See, I given you the definition. If all the poles of a given system are in the left half of s plane, system is said to be stable. If any one of the pole is located in the right half of s plane, then obviously system is going to be unstable, right? Then we have to see the next thing, that is if poles are there on imaginary axis. See, total s plane is divided into three parts. One is left half plane, another one is right half plane, another one is imaginary axis, right? So as of now we are concentrating on left and right, but not on imaginary. It's a special case. We will discuss that, right? Now suppose if I'm giving you one example like this, yes, this is a characteristic equation is equal to s square plus 2s minus 1 is equal to 0. It is a second order system. Second order system, if you want to find the roots of a second order system, you have to apply the formula minus b plus or minus root of b square minus 4ac by 2a, right? So s1 comma 2, it is going to have two poles, minus b plus or minus root of b square 4 minus 4ac by 2 into a. So s1 comma 2 is equal to minus 2 plus or minus root of 4 plus 4 8. So it is root 8 means 2 root 2. Yes, 2 root 2 by 2. It is minus 1 plus or minus root 2. So it is going to have two roots. S1 is equal to minus 1 plus root 2. So S2 is equal to, yes, let's find the value of S1 first. Minus 1. The value of root 2 is 1.414, I guess. Yes, it is going to be 0.414. And S2 is equal to minus 1 minus root 2. So then it is going to be minus 2.414. Now this system is having in fact two poles. This system is having two poles. In fact, the location of the poles, if you drop in the S-plane, one pole is there in the right half of S-plane. Yes, one pole is there in the right half of S-plane at 0.414. Another pole is at minus 2.414. What is the definition of a stable system? If all the poles lies in the left half of S-plane, system is said to be stable. But here in this case, one pole is there in the right half of S-plane, system is simply unstable. System is simply unstable. All these things every one of you know, right? Now, if I am giving this one third order, I am increasing the order. Characteristic equation is equal to s cube plus 3s square plus 2s plus 10 is equal to 0. If I ask you to find the stability of this system, it is not possible to get the exact location of roots. Why? Because third order system we are unable to solve, just like first and second order, right? Now, this is the reason why scientists called Routh and his friend Hurwitz, these two introduced a method called Routh-Hurwitz criteria to find the stability of higher order systems. So we will see the basic way how to form a Routh table, then the stability using Routh-Hurwitz criteria, then shortcuts of third order, fourth order, first and second order, or anyhow easy for us. We can find directly for first and second order. And one point I want to tell you very clearly here, that see, I will tell you, see, I'm taking some example. So suppose characteristic equation is equal to s square plus let me take third order only, s cube plus 3s square minus 2s plus 10 is equal to 0. You need not to calculate its stability, you need not to find its stability. Directly you can say that it is unstable. Why? Because there is a sign change between the coefficients. This is plus 1, this is 3, this is plus, this is minus. If there exists a sign change in the given characteristic equation between the coefficients, then directly we can say that it is unstable. Means my point is very clear here. I'll repeat the point, that is, if you take this system, if you see this system, there is one sign change between the coefficients of the given characteristic equation. This is plus 1, this is plus 3, this is minus 2, this is 10. There is a sign change. Now here there is no sign change. See, this point is somewhat confusing. I'll explain you very clearly. If there exists a sign change between the given coefficients of the characteristic equation, then that system is directly unstable. So it is already unstable. You need not to apply any RH criteria for that to find stability. Yeah, you can directly conclude that it is unstable. Suppose if I'm giving one characteristic equation like this, that is s power 4 plus 3s cube minus 4s square plus 10s plus 20 is equal to 0. Directly this is also unstable because there is a sign change. But here, sir, there is no sign change. Can I say that it is stable? No. If there is a sign change, we can directly conclude that it is unstable. But for this one we have to check further. We can't conclude. It may be or may not be. But it is for sure it is unstable. It is for sure it is unstable. But this one we have to check whether it is stable or unstable. So if you want to apply RH criteria for finding stability, first of all, that must satisfy some conditions called necessary conditions. In that, the first condition is there should not be any sign change between the coefficients of the given characteristic equation. And another one is, let me take one more example here. Suppose there is a characteristic equation that is s cube plus 2s plus 10 is equal to 0. Here s square term is missing. So if I write this one s cube, I can write it as 0 into s square plus 2s plus 10 is equal to 0. See, there is a coefficient which one is 0. If there is any one of the coefficient which is 0 in the characteristic equation, then also we can say that it is going to be unstable or marginally stable, but it is not going to be stable. Simply, I can say that it is not stable. See, there is a difference between unstable and not stable. Unstable and not stable. Yes. So it is not, for sure I can say that it is not stable. So for this one also you need not to apply RH criteria directly. You can say something that is it is not stable. Means the necessary condition to apply RH criteria for finding stability. See, I am repeating that word for finding stability. By using RH criteria for an unstable system also you can find number of RHP, LHP and J omega P. Okay, that is another application of RH criteria. But if you want to find the stability, only stability you want using RH criteria, the necessary conditions are there should not be any missing coefficient and there should not be any sign changes between the coefficients of the given characteristic equation, right? Yes, come on here. I am writing that is a necessary condition to apply RH criteria for finding stability. Yes, necessary condition. Yes, necessary condition. Right? What are those? Yes, what are those? I'll write here. There should not be any missing coefficient and there should not be any sign change. There should not be any sign change between the coefficients of given characteristic equation. That is, see, generalization I do mathematically. See, it's a big sentence, it's a very big sentence, but instead of that sentence mathematically, that is the beauty of mathematics. See, if you are speaking some 10 lines that can be represented in one equation, that's the beauty of mathematics, right? Yeah. So suppose I'm taking characteristic equation that is a s power n, a n s power n, or let me take it as a1 s power n. Yeah. a1 into s power n plus a2 into s power n minus 1 and so on, an minus 1 into s plus an is equal to 0. For this one, to satisfy necessary condition for further checking, that is Raoult-Hurwitz criteria, the necessary condition is nothing but a1 comma a2 and so on, an minus 1 comma an must be greater than 0. Yeah, all that sentence, this is all the coefficients must be positive, must exist. Greater than 0 means all are positive and all are existing, right? So that's all. So necessary condition. Now, how to apply RH criteria? I am taking one third order system. From there, a lot of shortcuts we are going to learn. Today, I'll complete a third order, how to apply generally and with shortcut, right? Both the ways I'll be taking up. I'm taking one example. Yes. So characteristic equation is equal to as cube plus bs square plus cs plus d is equal to 0 and a, b, c, d must be greater than 0. This is what? Necessary condition. That is what? Necessary condition. So if that itself is failed, see, sir, if b is equal to 0, that is not stable. Sir, if b is negative, directly unstable. You need not to check further Raoult-Hurwitz criteria for stability, right? Now, how to apply RH criteria? That is a simple method. See, that is R tabulation. See, first you have to take S cube. This is Raoult-Hurwitz table. Raoult-Hurwitz table. S cube, then S square, then S power 1, then S power 0. Like this you have to take. So what is the order we take in third order? Third order means how many rows you got. See, these are the rows. These are the rows. S cube is a row. S square is a row. S power 1 is a row. S power 0 is a row. For third order you have 4 rows. For nth order you are going to have n plus 1 rows. See, the number of rows in the R tabulation of any given characteristic equation are equal to n plus 1, where n is the order of the given characteristic equation. Now, see, carefully observe. S cube coefficient is a. First you have to start with this one. Then skip this one. Then you fill the next element. Yes, done. Skip this one. After that, nothing is there. 0. Right? That way you have to fill. This is, we are not calculating anything, just we are filling. We are not calculating anything, we are just filling. Now, as you take an S cube first, then S square next you have to take. You start here, this is going to be B. Skip this one, yes, then you take D. After that, nothing is there, you take 0. So, first 2 rows are directly filled. First 2 rows in the R tabulation are directly filled. We did not calculate anything. So, that is just filling. Now, next row onwards we have to calculate. The first step is always you start, I repeat, always you start with the first element of the latest row. This is the latest row and this is the first element. This is the first step. What to do, sir? Multiply these two. Then what you are going to get? BC, right? BC. Then second step is multiply these two. Second step is multiply these two. That is AD. Subtraction of those two you have to take by always this B will come in the denominator. Right? I repeat. First 2 rows are directly filled. First 2 rows are directly filled. Next row onwards we have to calculate. First step is this one. Multiply these two. First step, this is the first step. Yes, this is going to be BC minus subtraction of this one. This is going to be minus AD by always this element will come in the denominator in this particular row, whatever the element you are calculating. Sir, I want the next element. I want next element in the same row. Yes, again you have to start with this one only. Yes, B into 0, 0. Again this one. Yes, A into 0 minus 0 by this P only will come into picture. Always the denominator. Yes, 0 minus 0, 0 by anything is 0. So this particular one is directly 0. Nothing is there here, 0. No elements here. You can put zeros and you can calculate. Right? So this way we calculated the third row. Yes. Now I want to calculate the fourth row also. What I do is, for my simplicity purpose, let me take this one as some y. Okay. Let me write here as y. Okay. Here I put it as y, where y is equal to what? Y is equal to BC minus AD by B. BC minus AD by B. So now next how to calculate? Again you have to start with the first element of the latest row. This is my latest row. First element is this. Multiply these two. What it is? YD minus 0 by y. Y will get cancelled. Then you are left with what? D. See, this is 0, 0. Y will get cancelled. Then you are left with what? D. This is D. Right? So let me replace this y with AD minus BC. Okay, I am removing this first, second, and all. I explain you the steps. Okay, because it is looking clumsy here. BC minus AD by B. Right? So this way we completed the tabulation. Nothing is there here to put zeros, no issues, zeros. This way we completed the tabulation. Here one important point I want to tell you, that is this point is very useful when you are doing problems. Sometimes it feels insufficient data, but if you follow this rule, the data will be sufficient for you. Right? What is the last element of the characteristic equation? That is D. Right? That is there in the second row here. That is there in the third row? No. That is there in the last row. Right? So one point, very clear point that is here is for any R tabulation, the last row element of the R tabulation is the last element of the characteristic equation, and that last element is propagating from up to down by skipping one row. It is there in the second row, not there in the first row, there in the second row, not there in the third row, but there in the fourth row. Suppose it is there in the first row, it will be there in the first row, won't be there in the second row, will be there in the third row, won't be there in the fourth row, will be there in the fifth row. Like that, from top to down, the last element of the characteristic equation will be propagating from top to down by skipping one row, and this last element is always the last element of the given characteristic equation. So these 2 points are very, very important. Now, what is the stability according to Raoult and Hurwitz? Yes, first let's know that point. According to Raoult-Hurwitz, see, according to Raoult-Hurwitz, a stable system is what they are saying is if there are no sign changes, if there are no sign changes, yes, in the first column of route array, in the first column, of route array, then the system is said to be, system is said to be stable. So what he is saying, clearly you observe, he is saying, first of all you have to form route array, yes, route array or table, route or route array, both are same, this is the route array or route table. Now you have to select which column in that, you have to select the first column, yes. In the first column, what he want, there should not be any sign changes. Now observe here, A is positive or not, yes, when we are taking the question itself, we take in A, B, C, D are greater than 0, that is a necessary condition, yes, A is positive. B is positive or not, B is positive. D is positive or not, D is positive. Now, whether this AD, BC minus AD is going to be positive or not is going to depend on the values of BC and AD. If here three cases will exist, again three cases will exist. First case is if BC, the product of BC is greater than AD. BC minus AD is going to be positive, yes. Let me take in the next page, that is as case 1, yes, case 1. What is the case 1? Case 1 is you taken a problem or the examiner given a problem in such a way that if BC is greater than AD, if BC is greater than AD, S cube, S square, S power 1, S power 0, yes, this is A, this is C, this is BC minus AD by, this is B, not C, yes, this is B. This is AC, this is BD, this is 0, 0. This is plus, and this is D, this is plus. If BC is greater than AD, BC minus AD by B, this is also positive, right? That is also positive. Now, plus 2 plus, no sign change. Plus 2 plus, no sign change. Plus 2 plus, no sign change. Number of sign changes in the first column of route array. Number of sign changes in the first column of route array. In the first column of route array are how many? Route array is equal to 0 if there are no sign changes. System is stable. System is simply stable. What is the second case? Case 2 is if BC is less than AD. Yes, if BC is less than AD, yes, S cube, S square, S power 1, S power 0, right? S power 0. So this is AC, this is BD, this is BC minus AD by B, and this is D. This is plus, this is plus, this is minus. That is minus. And the last one is anyhow plus, you know. Now how many sign changes are there? People will count the sign changes as 1. No. Change means you have to calculate the from previous to next one. How many sign changes are there here? No. Plus 2 plus, no sign change. But plus 2 minus, yes, this is the first sign change. Minus 2 plus, this is second sign change. Yes, number of sign changes are how many? Yes, number of sign changes is equal to 2. Therefore, number of RHP, right hand side poles, is equal to 2. Here, I did not accommodate that point knowingly. Now I will tell you here, if a system is unstable, then definitely it is going to have some poles in the right half of its plane. See what is expecting, there should not be any sign change in the first column of route array. Then it is stable. If there is a sign change in the first column of route array, that is unstable. If it is unstable, means it is going to have some poles in the right half of its plane. Then if sign changes are present, in the first column of route array, yes, first column of route array, the system is said to be route array. Then the system is said to be unstable. System is said to be unstable. If it is unstable, there will be some number of right hand side poles. Yes, later there are some exceptions on the same topic. Later, see, if there are no poles in the right half plane but poles on imaginary axis are repetitive in nature, then it is going to be unstable. We will discuss those things. Number of RHP is equal to number of sign changes. Number of RHP is equal to number of sign changes, right? On the same grounds, yes, if it is yes, number of RHP how many? 2. Why? Because number of sign changes are 2. So this way we can find the stability of a third order system. Let's see some problems which were asked in the previous GATE examination. See, I'll tell you, I'll take the problems which were asked in previous GATE examination. Yes. Yeah. Now observe here carefully. Yes. Just I am increasing size of this problem. Yeah. If you observe this question, see, generally people will waste their valuable time in solving this question by applying RH criteria, but I will tell you not to apply RH criteria. What he is saying? A system described by the transfer function, this is H of S. H of S means, don't you think that it is going to be a feedback path transfer function. No, he said that transfer function means it is a closed loop transfer function. What is the characteristic equation you have? The characteristic equation is S cube plus alpha S square plus Ks plus 3 is equal to 0. What is asking? Is stable, he is saying that it is stable, okay? The constraint on alpha and k are, if this given system is stable, then what is the condition on alpha and k such that it is going to be remain stable, right? First of all, to check the stability with help of RH criteria, it has to satisfy necessary condition. What are the necessary condition? There should not be any sign changes between the coefficients of the given characteristic equation. From that one, what is the necessary condition? I can write from necessary condition alpha must be greater than 0 and k must be greater than 0. As it is third order, directly I am doing the shortcut, I am not applying RH criteria. What is that? S cube plus alpha S square plus Ks plus 3 is equal to 0. Compare this one with the AS cube plus BS square plus CS plus D equal to 0. For this one to be stable, what is the condition we got previously? Yes sir, previously we got some condition. Yes, what is the condition? Yes, BC, if BC is greater than AD, then I got it as stable. Yes, what is the next thing we got? If BC is less than AD, yes sir, system is unstable here. I forgot to write. System is unstable. Yeah, we wrote one point that if there are sign changes in the first column of authorized system is unstable. If BC is less than AD, how many sign changes you got? 2 sign changes. This particular system is unstable with 2 RHP, right? With the 2 RHP. Come back to the question what we are discussing. Yes. Now, what is the condition for stability? He is asking, he is saying that his system is stable. Then the condition is compare. A is 1, B is alpha, C is k, D is 3. BC alpha k must be greater than 3 is another condition. So alpha k must be greater than 0, alpha must be greater than 0, and k must be greater than 0. So these are the conditions to satisfy for the system to be stable. Directly, see, I didn't went for that RH tabulation. We are saving our valuable time, right? Now observe here, which one is satisfying? Which option is satisfying? Option A is absolutely wrong. Alpha k is less than 3. You see option B, alpha greater than 0, alpha k greater than 3. Okay, fine. Let's see. Alpha k greater than 0. No, alpha k must be greater than 3. Alpha k less than 0. Nothing. Yes, option B is suitable. Alpha greater than 0 and alpha k must be greater than 3. Right? So this way, without doing RH criteria, we can answer. Or, sir, I want to go with RH only. Sir, I want to go with RH only. That is up to you. S cube, S square, S power 1, S power 0. Right? Yeah. What is, shall we fill? Yes. This is 1. This is K. 1, K, 0. Alpha, S, 3. Alpha 3, 0. How much it is? Alpha K minus 3 by alpha. And this will be 3. So, anyhow, this one is positive. Alpha must be positive. Yeah, alpha must be positive. See, why? Because we want necessary conditions to satisfy. Alpha must be greater than 0. And this is positive. I want this one, 3 is anyhow positive. I want this one also to be positive. That is positive if alpha k minus 3 by alpha must be greater than 0. From that you get alpha k must be greater than 3. Alpha k must be greater than 3. This way also you can do. See, without doing all this, just if you remember BC greater than AD, stable. BC less than AD, unstable. That's all. Right? Let's go to the next question. Yes. It is 4th order. Leave it. Yes, it is 4th order. Leave it. Yeah. Let's do this question. He given, here also we will get one shortcut. That is the loop gain GH of a closed loop system is given by the following expression, that is k by s into s plus 2 into s plus 4. The value of k for which the system just becomes unstable. He is asking the value of k for which the system is going to be unstable. First of all, I need characteristic equation. What is characteristic equation? That is 1 plus gh k by s into s plus 2 into s plus 4 is equal to 0. Now characteristic equation is equal to s square plus 2s into s plus 4 plus k is equal to 0, right? S plus 4 plus k is equal to 0. Now expand it further, that is equal to s cube s plus 4s square plus 2s square plus 8s plus k equal to 0. So characteristic equation is equal to s cube plus 6s square plus 8s plus k is equal to 0. What is the condition for a third order system to be stable? What is the condition for a third order system to be stable? That is first of all coefficients must be positive. 1 is positive anyhow, 6 is positive anyhow, and 8 is positive. K also must be greater than 0. Yes, that is the necessary condition. Then what is the sufficient condition? That is 6 into 8, 48 must be greater than K and K greater than 0. These two are the conditions to be satisfied. That is 0 less than K less than 48, system is said to be stable. System is said to be stable. 0 less than K less than 48 means if the value of gain K is greater than 0 but less than 48, then the system is said to be stable. You don't have to go for RH criteria and all. Yes, you have to go for RH criteria and all. Let me see the options. Yeah, he is asking, it is see up to less than 48 it is stable, means 47.999 also your system is stable, but that is exactly equal to 48, it is not going to be stable. The answer is just becomes unstable. He is asking just becomes unstable. The answer is 48. The answer is 48. Actually, exactly for K equal to 48, it is going to be marginally stable. But here 96 is far away from 48. Even 48.00000001 also system is unstable. Exactly 48 marginally stable. 40 marginally stable. 47.9999 also it is stable. But from the given options, wisely we have to choose the option, right? So this way, third order system stability directly without pen paper you can find, and you can save your valuable time in the examination, right? So in the next discussion I will be taking fourth order and its extensions and shortcuts. So Engineer's Career Point is located at Chandigarh sector 34 में है. तो जून 1 से गेट ऑनलाइन और ऑफलाइन का बैच स्टार्ट कर रहे हैं हम लोग गेट का. So there will be a dedicated batch for online as well as offline. You can walk into our office which is located at sector 34 in Chandigarh, or you can call to the number that is provided in the description. Thank you.